Log on, tune in, find out. Another good idea from Cambridge.
It was very fashionable.
I'm glad that Radoslav, we've finally been able to pin him down to give us a talk. He's been so busy going around the country giving talks in other places that we couldn't manage to find the time before. But finally, he's going to talk to us about multiplicative algorithms for constructing d-optimal designs when there are linear constraints on the weights. Over to you.
So, thank you very much. At the beginning, a very brief overview of the talk. I will not spend too much time on basics, since you are all experts. I'll jump straight to DH optimality, a kind of generalized d-optimality of approximate designs, and the multiplicative algorithm for calculating of these generalized d-optimal designs. Of course, I'll point out connection to the standard d-optimality case. Secondly, I'll talk about constrained d-optimality. By constrained d-optimality, I mean the d-optimal designs with linear constraints on the design weights. And I'll show that it can be treated as a problem of this DH optimality, of this general optimality, which is very simple in a sense. Then I'll formulate something that I call the barycentric algorithm, which is a kind of multiplicative algorithm, and this already should be something new that among other things, I developed here during my stay at the Institute. Then I'll show essentially two selected examples, and the first example is d-optimally augmented designs. The constraints are of kind of lower bound on the design weights, and a more difficult example would be the d-optimal stratified design, something that I call d-optimal stratified design. And at the end, a couple of concluding remarks. So, what is the problem of DH optimality? Let us assume that we have a statistical experiment, a general statistical experiment with an unknown parameter beta, consisting of a series of trials, as usual, and an experimental domain X, which is finite. The experimental domain here will be finite. Of course, we can more or less transform even an infinite experimental domain to the finite case, so n can be very large, for example. It can be very large. An approximate design, as usual, is a probability measure on the design space X. Any design represents the proportion of measurements which should be taken, or observations or trials which should be taken in particular point small x. So the small x is represents the design points. Very good. Any design that is this probability measure can be represented by an n-dimensional vector of weights, of the design weights. So I will use the same notation, the same symbol, to denote the probability measure, W, bold W, and the vector of design weights, W. Of course, when the experimental domain is finite, we can represent it either by probability measure or by a vector. These vectors live on a probability or unit n simplex, which I will call or denote Pn. Now, for each design point, small x, we know some elementary information matrix that I denote Hx. So for each design point x, we have a elementary information matrix which is in a sense associated with this x and represents the amount of information which is gained from the trial in the point x. It should be a non-negative definite matrix for this talk. It's just non-negative definite matrices. And the sequence of all these elementary information matrices, which I call this calligraphic H, will be called the model. It is not the model in the standard statistical sense, but it's everything from the model that is necessary to know for our design problem. Okay, so there can be many statistical models, but what we need to know for the design problem is just the sequence of these elementary information matrices that represent the amount of information from each possible trial. And our fundamental basic assumption will be that for a design W, the amount of information about the unknown parameter beta obtained from the entire experiment, from all the trials, is proportional to the information matrix of this form. Okay. So the information is additive. We can calculate the information matrix, the information about the unknown parameter from the entire experiment, by weighing the elementary information matrices with weights given by the vector representing design, vector W. We will assume that all these information matrices, elementary information matrices, are non-zero, and we will also assume for this talk that the convex hull of all these information matrices contains a non-singular matrix, so that there is at least one non-singular information matrix of the entire experiment. By Pn plus h, I will denote the set of all regular designs. These are such designs that this information matrix, that the corresponding information matrix, is not singular. This assumption of additivity, this crucial assumption of additivity, is often satisfied for models with independent trials. The classical case, of course, is when we have the linear regression model, homoscedastic real-valued linear regression model of this form. This is the unknown parameter. These are the regression functions. Here, the elementary information matrices would be of this form. Notice, however, that these matrices are always of rank 1. Okay? In the classical case, the elementary information matrix associated with any design point is of rank 1. But in very many cases, for example, when the observations are vector valued, when we obtain a vector of observation from each trial, which is in practice very often the case, then we can use elementary information matrices, or should or need to use elementary information matrices, which are of higher rank, a general information matrices H. This is, of course, nothing very new, because it has been used many times before, although perhaps not with this terminology. In this talk, we will talk only the criterion of d-optimality, not about any other criteria defined in this form. So it's not logarithm determinant or something usual, but determinant of the information matrix to the power of 1 divided by m, mth root of the determinant of the information matrix. So it's not that we would like to minimize loss, but maximize information. Okay, we rather maximize information. So this is a concave criterion. It can be shown, many of you know that this is a concave function of the information matrix M. A design will be called DH optimal if it maximizes the criterion of d-optimality for all possible designs. And the corresponding information matrix will be called the DH optimal information matrix. This a little bit generalized problem of d-optimality, DH optimality, shares many nice features with the classical problem of d-optimal design with real valued observations and independent errors. It's been analyzed or treated in very many different sources. It's very difficult to trace back the original idea. In some sense, it's in some special cases, in some most important special cases, for example, for the vector valued observations, it's been known for a very long time. For example, in the book by Fedorov and Hackl, there's several versions, so to say, of this generalized optimality, of this DH optimality. But as such, this problem has been analyzed in the Dariusz Uczynski book and in one of my papers in Mathematica Slovaka. So firstly, there exists at least one DH optimal design, which is completely trivial because the set of all information matrices is convex and compact. It is essentially a convex hull of a finite number of non-negative definite matrices. And the criterion of D optimality is continuous. So it's clear that there exists at least one DH optimal design. Also, from the strict concavity of the criterion of D optimality, it follows that the DH optimal information matrix is regular, non-singular. By regular matrix, I mean non-singular matrix, and unique. Of course, the design itself does not need to be unique, but the information matrix, the optimal design does not need to be unique, but its information matrix is unique. There is a simple equivalence theorem for this DH optimality, which very much resembles the equivalence theorems, the theorem for the classical case. There are, for example, non-trivial upper bounds on DH optimal weights. You probably know that the D optimal designs, that the weights of the D optimal designs in the classical case are all at most 1 divided by m. Something similar can be shown for this DH optimality. Although in this case, the optimal design can be even singular. Even with a large dimension of the vector of parameters, the optimal DH optimal design can be singular, because we work not only with information matrices of rank 1, but with general information matrices, and the optimum can be achieved at some singular positive definite information matrix. So we will frequently use this variance vector of any design, any regular design W, which is defined very similarly as in the standard case, but here we need to use a little bit different form with trace. Note that if Hx would be fx transpose, where f is the vector of a regression function, then this would boil down to standard form of the variance function fx m information matrix to the power of -1, inverse of the information matrix, times fx. Okay, so this is a vector with components of this form. Perhaps I should stress that I denote the components of each vector by parentheses. Okay, so this means the x component of some vector. We will see it, for example, here. This is the x component of this vector. So I will not state equivalence theorem, but something stronger. If we have W a regular design and W star is a DH optimal design, some DH optimal design, then this inequality gives a lower bound on efficiency of the design W. I rather like thinking in terms of efficiencies and bounds on efficiencies, not just equivalence theorems. Of course, this inequality immediately gives an equivalence theorem, because if this is satisfied, then the efficiency is 1, that is, W is D optimal, DH optimal, if and only if this ratio is 1, that is, if and only if maximum of this variance function, variance vector, is equal to m. So it immediately implies the equivalence theorem. But the equivalence theorem itself does not tell us much or anything about efficiency, about the quality of a suboptimal design. And in practice, we don't need to strive for absolute optimality, completely optimal designs. We often can do with designs that are not optimal but are good. And these bounds on efficiency, lower bounds on efficiency, can help us judge how good are all design or any design, or give some bound on how good how good they are. They can also help us, for example, to stop an algorithm for constructing the optimal design, and so on. So I rather like to give bounds and efficiency and not equivalence theorem, because the equivalence theorem is only about the absolutely optimal designs and not about something which is good but suboptimal. Moreover, I think that these efficiency considerations may be very important for exact designs. I will not talk much about exact designs, just a little bit, at the end perhaps, because it's connected to exact designs, related to exact designs very much. Because it's very difficult to calculate exact designs optimally. That is, for most models, for most normal models, it's almost hopeless or very difficult to find the exact, say, the optimal design such that we are certain that the design is the optimal. But it might be much easier, much easier to construct an algorithm, for example, which gives you a design with guaranteed efficiency, say 90%. Okay? It's very different to construct an algorithm which calculates absolutely optimal design or solve a combinatorial optimization problem completely, and to give an algorithm which provides guaranteed efficiency of the solution, which can be very high. Okay? So I think that the people should think a little bit more perhaps in terms of efficiencies. The second part of the theorem is based on these my paper with Luc Pronzato, essentially, and then it was generalized very easily in this paper, in the second paper. And it says, how can we simplify the problem substantially in many cases? H is some function of a positive number epsilon. We do not need to understand why the form of the function is this. But if we have any d-optimal design or dh optimal design in this sense, with non-zero y component, then the variance function in the point y of any design y, w, must obey this inequality. Perhaps it's a little bit confusing, but simply, if this inequality is not satisfied, this is a better way of stating it. If this inequality is not satisfied for any given design W that we know that does not need to be optimal, then we know that the optimal design must have the y-th component exactly 0. Okay? And we can remove this component, this design point from the experimental domain. Using this, we can sometimes remove, say, 99% of the experimental domain, okay? Which amounts to a 100-fold speed up in computation, for example. Okay, so this is some a non-trivial theorem that perhaps you don't know. So I explicitly showed it here, that it can be adjusted to the general problem of DH optimality.
But to verify this inequality, you still need some computations.
Yes, I need to find the maximum of the variance function, because it only depends on the maximum of the variance function, nothing more.
But you simplify algorithm after doing quite a bit of computations. That's what I mean.
It's not that big computation. For example, if I would use your algorithm, Federal-Green algorithm, I would need to find this point x which maximizes the d function anyway. And then I can just plug it here. No more computation is required if we do not count these square roots and this very elementary function as a computation. Okay? And then I just go point by point and select which of these can or cannot be excluded. Sometimes very many of them can be excluded, And then the experimental domain reduces, and the subsequent maximization with a reduced design space X will be much simpler. Okay? So the DH optimal design, similarly as the D optimal design in the classical case, can be calculated by a kind of by certain multiplicative algorithm, so-called multiplicative algorithm, that is defined or given by an updating rule. Which is an updating rule? It's something that to one design assigns another design. It's an operation, a map on the space of all designs. Defined by the following simple formula. This means just the diagonal matrix with this vector of weights on the diagonal. So the X component, say, of the new vector of weights is just a multiple of the X component of the previous weight and the corresponding value of the variance function divided by m. It can be shown that this transformation keeps the constraint. I mean, it keeps the constraint that it sums to 1. It's not completely obvious from immediately, but it can be shown that this transformation operates on the space of designs. That is, if the argument is one design, then the result is again a design of proper design of proper vector of design weights. What is much less trivial is that this transformation TH for the standard case, but also for this DH optimality, is monotonic. That is, if we have some information matrix, a determinant of the information matrix of design W, then the determinant of the information matrix of the new design in the sequence, THW, is at least as large as the determinant of the previous information matrix. That is, it's monotonic in the sense of increasing determinants of the information matrices. And we can generate designs. We need to start with a regular design and then generate design W2, W3, and so on by just application of this updating rule TH. And what can be shown is that not only it is monotonic, by the way, there are a couple of proofs, all of them not trivial. The first proof appeared in the Dariusz Uczynski book that I was not aware of, and then a second proof of this generalized version appeared in our paper, but the proof is completely different. Anyway, it's well established that this algorithm is monotonic, and moreover, it's not only monotonic, but the sequence of information matrices converges to the D-optimal, DH optimal information matrix. The proof is quite subtle. And I would say that some proofs in the past would require some points to be clarified. So I think the most careful proof appeared only quite recently, and it's in a paper in Annals of Statistics by Yaming Yu and a rising star in design. So now we will focus on constraints, on the design with constraints. We will assume that our model H is just the classical model. That is, we have some vector of regression functions f, and the elementary information matrices are of this form, of the classical form. Now, let Qn be a convex polytope. The aim is to find a design W star belonging to this convex polytope, which maximizes the value of the criterion of d-optimality within the designs in this convex polytope. Why am I talking about convex polytopes? It's because all linear constraints on weights define a convex polytope in the space of designs. So any inequalities of the kind like the space of feasible solutions for linear programming, that is of the type matrix A times W, equals or is less or equal to b, they amount to defining some convex polytope in the space of designs. Now, of the utmost importance for what I'll talk about are the extreme points or extreme vectors of this convex polytope. So let's say matrix W, matrix Q is the matrix of all the extreme vectors of this convex polytope. Since the function mh, that is the function that to a design assigns the information matrix, is linear, then it transforms the convex polytope Qn to a convex polytope in the large space of information matrices, in the space of information matrices. That is, we arrive to a polytope which is generated by some number of information matrices of this form. The number is the size of this number of is the number of these extreme vectors. Thus, simply, the problem of linearly constrained D optimality is equivalent to the problem of DH optimality or DH H tilde optimality, where H tilde optimality, H tilde is a model which consists of these information matrices of the extreme designs, extreme vectors, but extreme designs. It can be seen as extreme constraint designs. Okay? So simply we have a general problem of DH optimality, by solving which we can arrive at these constraint designs. Of course, this is again not new. This is quite trivial, and some hints along these lines can be already found in Henry Wynn's paper or Ben Torsney paper, and so on. So, perhaps I should point out that there is a very simple relation between the D function of some design W and the D function of the corresponding design W tilde. What is W tilde? If W and W tilde are related using this simple equation, then the corresponding information matrices in the corresponding models are the same. But what does this mean? This means that if we have a design W which is inside of this constraint set, then W tilde is the coordinates of the design W that are expressed that express W using the extreme vectors of the set Qn. Okay, so this is just coordinates. Perhaps I should draw a picture of there will be some picture in the sequel, but let's say that our constraint set is like this, and we have some W, okay, some design W in this constraint set. Then, and these are extreme vectors, Q1, Q2, Q3, Q4, Q5. So what is the relation between W and W tilde? W tilde is simply the coefficients of these of the convex combination that express W using the vertices Qi. Okay, so for example, this might be 1 divided, well, some number between 0 and 1, another number between 0 and 1, and so on, such that they together sum to 1. That's W tilde. And the relation between these D function is as follows. We can skip this theorem. This theorem simply states what is the efficiency, a lower bound on the efficiency of any constraint design W within the set given by the constraints. So, in principle, the D-optimum constraint design can be computed by the multiplicative algorithm for DH optimality. So that I could simply find, possibly, all the extreme vectors of the constraint set, and then construct these elementary information matrices for all these extreme vectors, and run the multiplicative algorithm for DH optimality, or DH tilde optimality in this case. But usually this causes numerical problems, or is completely outright impossible to do. Because in very many cases, in very many situations with constraints, the size of the number of the extreme vectors is huge. It can be trillions, for example. Okay, it very well in very simple problems the size can be, say, trillions. And moreover, the algorithm would need to calculate with compute with matrices of size m times m. M can be like say 10 parameters. So working with a trillion matrices of size 10 times 10 is not very simple. Okay, so it somehow the problem needs to be tackled differently. The key idea is that under the linear constraints on weights, we can use this multiplicative algorithm. We really can use it, but only implicitly, not explicitly. We do not need to evaluate all these. We do not need to store, for example, all these trillion of extreme points, a trillion of matrices of size m times n. We do not need to calculate with them directly. They are not in the program, they are not in the memory. We just use them mathematically, implicitly. And the actual computations are only with the constraint designs in the primary space. So, very briefly, we need to operate with two functions. The first function, italic w, is defined by this formula. That is, if we have some convex combinations of these extreme vectors, the w tilde is the coefficients of the convex combination, then the function w tilde, the italic w, gives us the resulting point inside of the constraint region. Okay. Next, we need to work with a function w tilde, which is much more complicated in general. It needs to be continuous, firstly, and secondly, it needs to satisfy this equation. In simple problems, it would be the inverse of w. Okay, but mostly the size of this and this space very much differ. It cannot be the inverse. It only needs to satisfy this inequality. How to explain what this function w gives? It's not so complicated. Assume that we have a given vector w inside of the constraint space. This function w tilde would give you a vector of convex of components of the convex combination that result in the vector w. So, but the problem with this is that that usually this function w tilde is not unique. Simply, we can have many different convex combinations of these extreme vectors that result in the given vector w. This is one. But second would be, for example, this and this and this, and zero, putting zero weight to these two extreme points. Okay? So we can re-express a given design in the constraint region by very many different convex combinations of the extreme vectors. Okay? So that's difficulty. We need to find a suitable function w tilde that expresses a given constraint vector by some convex combination of the extreme vectors of the extreme designs. It's, okay, so essentially what I've written here is at this picture. Usually this map is nonlinear and is not unique. And it's a crucial point for application of this method. Using this function w tilde, and the multiplicative algorithm or multiplicative updating rule on the space, on the large space, I will call it a large space, we can define the so-called barycentric, that I call barycentric updating rule. Perhaps we should look at this picture, just at this picture, this scheme. So, first, we begin with some design, with some constraint design. This design lives in the space Qn. And we apply the function w tilde. That is, we re-express this design using the, or express this design using the convex or a convex combination of the extreme vectors, by which we obtain some design in the large space. Then we apply the multiplicative transformation in the large space to obtain some other design, a design that will have that will be better in the sense of the optimality, because it's the property of this multiplicative updating rule. But then we apply the quasi-inverse of this function w tilde to get back to this original space of weights, of constrained weights. Okay? So we simply get to this large space with million information matrices, elementary information matrices, a trillion, make the update by this very complicated and updating rule, but then we get the result and get back with this result to our small original space. Okay? And we do not need to perform these computations actually. We only we can express, like by an analytic formula, how would this transformation from W1 to W2 look like in the original space, okay? If this function w tilde is properly chosen. It can be shown, I showed that the sequence of the corresponding information matrices converges to some, it is monotonic, the sequence is monotonic in the sense of determinant, because both these transformations, they keep the information matrix. Simply the information matrix of this design, and this design, this design is the same. This design, this, and this design is the same, and so on. So these W's, they keep the information matrix. And since this transformation th tilde increases the determinant, then it's clear that this barycentric transformation in the original space also increases the determinant. That is, this is really monotonic. But it can be shown that it converges to some m infinity, to some information matrix. Unfortunately, it's not clear whether it converges to the d-optimal information matrix. It can be shown, but just for particular cases. Okay, so some example, the first example. Assume that we have a vector of with non-negative components that sum to a number less than 1. And our constraint design space, Qn, will be simply all the designs that sum up to 1, such that each component is greater or equal to corresponding component of the vector b. That is, we have vector b might be composed of this, say, lower bounds, and any permissible design needs to assign a bound that is at each component is at least as large as the corresponding components of the vector b. This is related to the problem of design augmentation, okay, which is treated in length in chapter 19 in the book of Professor Atkinson. in this case, the set of all extreme points is very simple. And in fact, the matrix of all the extreme vectors, extreme probability measures, extreme designs, can be written in this very simple form. This bold one is just the vector of all ones. And since it's so simple, I will skip this theorem because it states just what's the lower bound on efficiency in this case. Since it's so simple, we can define the quasi-inverse as a normal classical inverse, because this matrix that is composed of extreme vectors is invertible, simply. So we can define it as an inverse, and we have all the necessary components for definition of this barycentric transformation. We do our algebra. It's not completely nice and straightforward, but after a couple of pages, say, we can arrive at the following formula for the updating rule. So this formula has the property that if we start with some design W that obeys these constraints, then the next design, which would be obtained using this formula, again satisfies these constraints. It doesn't jump out of the region of permissible designs. And notice how simple it is to calculate the next point in this design space. That is the new design, new updated design. It uses just the D function. This is the classical D function. The vector B and some normal multiplications and component-wise multiplications. This dot in circle, it's just a component-wise multiplication. So this is extremely simple to implement in matrix-based languages such as MATLAB or R. It's just one line. Okay, the actual update of the weight is just one line, and it can be shown. In this case, it's quite simple. That the sequence of designs generated by a successive application of this barycentric updating rule, that the sequence of designs converges to the D-optimal design, but of course D-optimal in the constraint set. Okay. So this was a simple example. A more difficult example is something that I call D-optimal stratified designs. Assume that we have a decomposition of the experimental domain X into some strata. I call them strata, X1 to Xk. So in this case, this is the design space, and we have some strata, say just two, X1 and X2. Okay, and this together, they form the experimental domain X. And we also have some numbers, some positive numbers, then sub up to 1. Our constraint set is the set of all designs such that the weight assigned to all points together in X1 is S1, in X2 is S2, and so on. Okay? So that we decompose the region into subregions and require that the weights of the design in each subregion sum to a given number S as J, okay, for the Jth subregion. The most important special case is the case of so-called marginally restricted designs. But sometimes this design space, for example, can be of this form. Okay, it can be like a grid in plane. That is, we have two factors, one factor and second factor. Okay, these are the levels of the factor. Okay, so continuous level factor. And in some applications, we need to we know the sum of the design weights for each level of one of the factors. So, for example, our restrictions, I won't go into details of examples, but we know in advance what should be the sum of each valid each permissible design for all levels of one of the factors, okay, taken or understood as a strata. But it's not the single important example. Another important example is when we just fix some weights. Okay, when we assume that when we require in advance that a weight in some points should be given, okay, then this also is the stratified approach also allows us to analyze this very specific constraint problem. Okay. So, in this case, the set of all extreme vectors is much larger. Assume that x tilde is a vector of x's of the design points, okay, such that jth component of this vector belongs to the jth stratum. Anyway, well, without going into details, the size of the set of all extreme vectors, of extreme points of this constraint set, will be of this form. That is, the number is the product of the sizes of each of the stratum. So here, for example, the size of the design space of the set of extreme vectors would be, this is 5, so 5 times 5 times 5 times 5, which is already very large. But assume that you have 10 points here, 10 points here, and 10 levels of each factor. Then the size of the large design problem would be 10 to the power of 10, okay, which is impossible to treat directly. Again, in this case, we can formulate some kind of lower bound or some lower bound on the efficiency of a given design within the constraint set, and of course, it implies an equivalence theorem. Equivalence theorem, for example, as a special case for these marginally restricted designs, which were given originally in Cook and Thibodeau, okay, in a JSA paper about first paper about marginally restricted designs. And I also would like to mention the book by Federer and Huckel in chapter 4, which is devoted solely to constraint designs, and although it's not completely directly related to this, but it helped me a lot to verify, for example, my results using this DH optimality. So I consider it good to mention because it was of much use. Here, it's not completely straightforward how to define these function W tilde, such that we would obtain the barycentric coordinates using this W tilde. After some time, after some speculations, I arrived at this form, and it can be shown that this really gives barycentric coordinates for our constraint design problem, well-defined barycentric coordinates. But notice that it's nonlinear. It is not linear in W. Far from it. It's just some product of these W's. Okay. And again, when we have all the components, the function W, the multiplicative rule in the large design space, and the backwards function W tilde, if we all have them, then we can do some algebra, and we arrive at the following barycentric multiplicative rule. It looks a little bit complicated, but notice that it's much easier than using the original large space, the large space with, say, 10 to the power of 10 of matrices of size 10 times 10. Okay? It operates only on the space, on the original space of the constraint weights. K, the matrix K, is simply a matrix with zeros and ones, defined by it's exactly 0, exactly 1, if the xi belongs to x to the stratum x xj, and it otherwise 0. So it's a relatively small matrix. And S is a vector of our constraints, these S1 to Sk. And again, using some matrix-based computational tool, such as MATLAB or R, this is a matter of one line, because it can perfectly quickly calculate with normal multiplication as well as component-wise multiplication. So, such a simple rule not only that gives us something that with increasing determinant, the subsequent application of this barycentric algorithm gives us a sequence of designs with monotonic determinant, but as again can be shown using some subtle arguments. It's not so simple, but it can be done. It converges to the d-optimal design in this constraint design space. So subsequent application of this barycentric algorithm converges to the d-optimal stratified design. Okay, nice. So some further notes. We can combine all these barycentric algorithms with multiplicative, with deletion rules. I showed you these, the theoretical statement upon which it can be based, but I did not show you how these deletion rules would turn out in these barycentric algorithms, but it can be combined with subsequent significant speed up of the algorithm. It's also very probable that it can be fine-tuned and improved in many different ways. For example, using a clustering approach, such as in a paper by Raoul and Ben, or with a combination with other optimization methods, such that in another paper in computational statistics by Yaming Hu, he was able to improve by the so-called cocktail algorithm the speed of these multiplicative algorithm, essentially, or classical algorithms for calculating the optimal design very much, several orders of magnitude. And it's very probable that further research will show that these barycentric algorithms could be improved in a similar way. Another point, another note. For the specific problem, particular problem of stratified d-optimality, it is possible to suggest a different multiplicative heuristics that is a generalization of the heuristic in the paper by Raoul, Ben, and Jesus in a paper in Journal of Statistical Planning and Inference. And, well, I did the generalization, and I compared these heuristics with my barycentric algorithm, and I found out that this heuristics is faster. So I was a little bit disappointed, perhaps. But we should keep in mind that these heuristics is also simple to evaluate, but there is no theory behind it. It's very difficult to prove not even convergence, but not only monotonicity. Even monotonicity is very difficult to prove, and there is no such proof. Even the authors admit it in the paper. Okay, so this is faster in this specific case for stratified d-optimality. But my barycentric algorithm has proven convergence, proven monotonic convergence, and moreover, this stratified d-optimality is just an example of how to use the general method. And for other types of constraints, for example, for these, for these augmented designs or for cost constraint designs, I of course skipped many things that some things that I've done. For example, I've done on some other different kinds of constraints, so-called cost constraint, for example. And for those different constraints, there is no such simple heuristics, at least nothing simple that one could come up with that would work. Okay, it's just specific heuristics for this stratified d-optimality. While this approach of barycentric multiplicative algorithms can, in a systematic way, give us monotonically convergent algorithm. And so, in many practical problems, we have some linear constraint on the design weights. There is a survey paper, a nice survey paper by Cook and Federer from 1995. It was published in Statistics, that is solely devoted to constraint design problems. But it was not my real motivation, essentially, to do these constraint algorithms. My original motivation comes from the problem of computing exact designs. It turns out that for some nice, and I think perspective class of algorithms, perspective for design of experiments, which are similar, very closely related to branch and bound algorithms. Okay, the calculation of the approximate constraint designs is crucial for application of these exact design algorithms. In a sense, they form these constraint approximate design problems, form a link between the areas of approximate designs and exact designs. Okay, so that was my primary motivation. And since I perhaps do have 3 minutes, I can explain how the idea how, well, very roughly, because it would require another talk, but just the essence, how could these constraint problems of approximate designs be related to the problems of exact designs, for example, to the problems of block designs with block of size 2, because many of you are more interested in, for example, block design, with these exact combinatorial designs. So I should rely that you know something from Professor Bailey's talks. So if we have some treatments, for example, now we have 6 treatments, then the block designs with blocks of size 2 can be represented by a graph which is called a concurrence graph. Say this would be some concurrence graph, which says that these two treatments occur in one block, these two in another. This gives you how the block design looks like with blocks of size 2. And we can define some information matrix of such block design, and we can try to maximize not exactly determinant of this information matrix, but the product of all non-trivial eigenvalues, so to say, because the information matrix would be singular. So we need to specify something like something a little bit different than the criterion of d-optimality, but very closely related. And finding the d-optimal design for such setting, that is, finding the appropriate graph with given number of edges and given number of vertices, is a complicated combinatorial optimization problem. Okay? And when do the constraint algorithm enter the picture? Assume, for example, that you have some design. Well, if you just calculate the approximate design with all possible design points, because any couple forms a possible design point, then you would obtain just a uniform design. Something that tells you to perform 1 divided t choose 2, if t is the number of treatments, proportion of experiments for each combination or for each pair of treatments, which is of no use. I forgot this. Which is of no use. Okay, it can be it's very difficult to round to an exact design. But assume that you have the following constraints. Assume that you constrain that this weight. I will draw a different picture. Assume that you constrain that this should be exactly weight 1, that corresponds to 1 observation. this should be, and this should be, say. And you also can prohibit some weights. That is, you require that this is 0, that there will be no comparison of these two, and this is 0. There will be no comparison of these two. And now you calculate an approximate design, approximate d-optimal design, with these constraints, requiring that here will be one observation, here one, here one, here one, here 0, and here 0. And whatever the number of other observations or other combinations of treatments. Assume, as is often the case, that the resulting approximate constraint d-optimal design will have the value of the criterion of d-optimality worse than some known exact design. Okay? You have some benchmark, some exact design, some known exact design, and assume that your approximate optimal design with these constraints would be worse than the design that you already have. What you can tell? You can exclude all graphs with this, so to say, mask or template. No exact graph with no exact design which compares these two, and does not compare these two, and does not compare these two treatments can be the optimal. Because even the approximate d-optimal design on the set of all design with these constraints would have the value of the criterion worse than some design that you already know. It's a little bit complex perhaps to explain, so it's I don't know whether I am successful. But simply using this calculation, this computation of the approximate constraint design, you can exclude sometimes an astronomically large number of possible graphs, that is, of possible exact designs to evaluate the criterion of d-optimality and to compare with other designs. Okay? And this idea can be put to work using some kind of so-called branch and bound algorithms. Okay. Thank you. And thank you very much, not only for attention, but for having me here, for inviting me here to this perfect environment among these perfect people. Thank you.
Very much so. And thank you for that wide-ranging talk. So now, questions? Heiko.
Could you go back to your slide where you presented the barycentric algorithm first? So could you say a little bit more? Because, I mean, you start at the top, you go to the, say, large world, then you do something in the large world, go back to the small world. So it's not entirely clear to me why you could not just derive your transformation TH in the small world directly. Why do you have to make at least virtually that excursion to the...
because if I just apply the classical transformation here, it would jump off the constraint design space. Simply, I would not keep it without the constraint design space. So this is the small world, okay, the small. And I have the constraint space Q here. Okay? Say that I'm here with my design W. If I apply the classical transformation, multiplicative transformation, I could very well come somewhere here, jump outside of the constraint region. It's not possible to apply the classical transformation directly.
But you said why not stay in the small space? Why do you have to go back to the big space? Isn't that what you said?
No. I think I was wondering if you could get this THB at the top directly without having to make this excursion.
No, it's well.
You can.
I show that you can do it,
Yeah.
as expressing it using formulas, but not just using direct classical multiplicative update. Okay, you can do it in this space, and I do it in this space. I don't calculate with these millions, for example, of extreme points. I calculate with this with the weights in the original space. But theoretically, to derive the formula for this for this update in the small space, I go through this large space, okay? Which, for example, lets me control that it does not jump off the constraint design space, and moreover, it keeps monotonicity of the algorithm, okay?
Any further questions?
Yeah, this is a question about your last thing about branch and bound. I
Yes.
appreciate you weren't, in fact, of course, giving us a complete algorithm or anything, were you? But what happens when your approximate design is better than your design, your benchmarking design?
Very good question, but then we are going close to explanation of the algorithm itself. But very good question. If the approximate design,
A crisp paragraph would be.
if the optimal approximate design is better with respect to criteria of de-optimality than the exact design that we already have, then we make further constraints. So, for example, if for this case, for these constraints, okay, the approximate de-optimal design would be better than the exact design that we already have, then we make another constraint. For example, I say, using some tricky rules, for example, that I'll constrain this weight to 1 and calculate another constraint de-optimal design. Of course, by constraining it further, the space of constraint designs shrinks, the space of permissible design shrinks, and the maximum value of the criterion of de-optimality may go down as well. Okay? Even it may be, after this calculation, it may be worse than already the design that we have as benchmark, the exact designs. So we add, in a systematic way, we add those constraints until we are worse with the de-optimal approximate designs than the benchmark design. Okay?
Mhm. And you can do that in such a way that you can be sure that you partition the complete space. Is that-
Yes, exactly.
Yeah.
I can do it in such a way. Yes. I just stop at some point because at some point with this partitioning, because the point is determined exactly by the value of the criterion of de-optimality for approximate designs. Because then it tells me that at this point, I do not need to go further.
Yeah.
Because everything that is below this point is worse than something that I already have.
Thank you very much.
So I have a question about this. If you permute the treatments in here, you're going to get something with the same criterion. So does your searching take any advantage of symmetry so that it doesn't have to keep looking at things that are isomorphic?
It's another very good question, and I can answer it because I've already programmed this algorithm. No, this algorithm, this idea per se, as I explained, does not make use of the inherent symmetries in the problem. And it's true that if these symmetries are in some not so trivial way incorporated into the algorithm, then the algorithm calculates much faster.
That's what I thought.
Yes, yes. So these using the space of symmetries inherent in the problem can make the algorithm much more rapid. And it's not completely trivial to include these symmetries. So some algebras or group theory must be used at some point in combination with this algorithm.
That's why I asked, because I have a colleague who does all his calculations using GAP, and he always uses the group theory to cut down.
Yes. That's one way. One, of course, does not need to enumerate all designs, just a representative from each class of isomorphisms. Okay, but this is another approach how to further eliminate the space of all graphs that needs to be verified. And the crucial point is just calculating of the approximate designs with some constraints.
Any other questions? Heiko again?
I mean, just another question about a possible application of your stratified result.
Okay.
So if one is looking in the context, say, of response surface design, then you would be looking at three-level designs for a quadratic model. Then you could say, okay, referring to classical central composite designs, okay, I want to have a proportion for axial points with such and such, so that would be one of the curly axis,
Okay.
one for factorial or fractional factorial part, and one for center points, and then see what sort of design you get. So in cases where theoretical results are known, whether you then basically can reproduce them, and in cases where you then would choose different proportions of these three different components.
Yes, you're right, you're right. These stratified designs are simply suitable for any, for very many of similar problems. It didn't occur to me to use it for central composite designs, as you mentioned, so thank you, but yes, you're right. Perhaps it can be used in very many other situations. For example, when you just want to make it more robust with respect to knowledge of model. Okay, you can somehow stratify the experimental domain and say that I need to perform for the model verification at least some part of experiments here, here, and here. Okay, and then I found the optimal designs within these constraints of this data, which would satisfy, which was in a sense cover the entire design space in a uniform way, while at the same time considering or taking the criterion of d-optimality into account.
Any more questions?
This is just a comment. I seem to remember a long time ago Roger Mead talking about the kind of experiments they did in the West Indies, where hurricanes or tornadoes or something might come through. In that case, those really would be spatial coordinates, and part of your field might just be swept away by something. And then might well want to be all over it. That's just.
I just want to make a couple of comments before we thank Radoslav. One is to apologise. I don't know if any of you noticed, I only realised too late that I forgot to tell everybody to turn their phones off. And that's why I'm afraid we had some interference with the picture. So my apologies for that. The second is we have another seminar planned for the morning of Tuesday the 20th of December at 10 o'clock when Jordan Coe is going to talk to us. So put that in your diaries, and if anyone else would like to offer a seminar before we all depart, then please come and see me as soon as possible so that we can get a room booked and get it all put on the board. And now please join me in thanking Radoslav.